work your way around. Here's a triangle. So how many degrees inside of that triangle? So once, twice, 3 times, 4 times, 5, 6, 7, 8. So there's 8 triangles inside of a decagon. Each triangle has how many degrees? 180. So this is just angle addition. So this angle here plus this angle here make up that vertex angle of the decagon. So that's how we can get away with adding all of these smaller triangles together. Every single one of these little triangles, angles here, add up to that particular vertex. So we have all the vertices of this decagon accounted for. So what's 180 times 8? One 140? 1440. Oh, okay. What's 8 times 100? 800. What's 8 times 80? 64 with a 0. So 800 plus 640 is 1440. Use the distributive property to multiply that stuff in your head. It's faster than a calculator once you get your head going. Okay, so there are how many angles that we have to look at here? There's 10 of them. So each of these vertices, if they were all equal measure, would be how many degrees? 144 degrees. Yeah, that's if it was a regular decagon. Now, I don't remember, did they ask you to come up with the number of degrees for each angle or the sum of all of the angles? Okay, so 15 is the sum, and 16 is the single. Yeah, Hayden. What is the definition of a rectangle? Two pairs of parallel sides? And 4 right angles. Yeah, I think that's pretty much it. Read the word again. Regular, yeah, and I said this a few times yesterday. Regular meaning all the side lengths are the same length and all of the angle measures are the same measure. That makes it regular. This is a regular pentagon, a regular hexagon, a regular triangle, a regular square. I have no other figures here. But regular is same size side lengths, same size angles throughout. Okay, so now, you have any questions for me after this one? Your work? Could I see your work when I come around, please? I'm sorry. So many people have different answers. We need to talk this out.
When they're like, I don't know how to understand.
Which question would you want to ask a question about? I'm asking a question about number 14.
Yeah.
Oh, I said they all.
So the question they are asking is how are measure of angle W, the measure of angle Y, and the measure of angle Z related? So some of you may want to ask a question about how to answer that one and not know what kind of buzzwords to use. Here's your diagram, yes? If you get to that point where you can't use any words to describe what your question is, that are part of our vocabulary, then you might say something like, I do not understand what they are asking for. That's like real open-ended, rather than saying, I don't get it. I just want to get away from I don't get it. Because that's not a question, right? You do not see how they are related. Yeah. Phoenix?
Just a quick question. Supplementary angles may be equal 180.
Yes, supplementary add to 180. Yeah, that's a fact, right? So we have all these facts about the relationship between lines. A linear pair is you have a line and then a ray that comes off of it, those two angles together. For example, this, number 1 and 2, that's an example of a linear pair.
Yes.
So for 13, what are you going to say, Hayden?
They're a linear pair.
But there's 3 of them. 13 there.
So for question 13, the measure, I'm going to draw this up here, okay? A little bit bigger so that we can see it. And then they say we've got X, Y, Z, and W. Okay. So for question 13, the measure of W and the measure of X, you said that they're a linear pair, but a linear pair technically doesn't say anything about measures. It says that it's an angle formed by basically cutting a line into two different angles. So X and W are a linear pair. Because if we just cover up all of this and we look at it, they have a common side, and their uncommon side makes a line. So here's the common side between 1 and 2, and then here's the line which is a part of the uncommon side. Yeah, so X and W are a linear pair, but what about their measures? Okay, they're supplementary. Can you write that in algebra? So going back to 13, if you don't have an algebraic expression written down, add this in. What kind of numerical and algebraic relationship can we put together that describe these two? If we said the measure of angle X and the measure of angle W, what can you add to that to make a true statement?
Oh, measure of angle, W plus that is equal to.
Say it again?
For a plus sign is equal to the equal line.
Okay. So you put a plus, and then what else do you have to add, Lucia?
180.
What are they equal to?
180.
180. Good, so you need to be that loud, because I can't hear you half the time. I'm listening to that fan, I'm listening to that fan, and we're all talking through analysis.
Don't listen to the fan.
Huh?
Don't listen to the fan.
Well, so X and W add to 180. So this is what works for 13. Now for 14, you're supposed to relate X, Y, and Z.
No, W, Z, and Y.
Oh, really? Oh, W, Y, and Z. Oh, not X, Y, and Z. X, Y, and Z added together make 180, right?
Yes.
So then how do you relate W, Y, and Z? Huh? They don't have a relationship? You don't see a relationship yet. But there's a relationship. Everything has a relationship. Everything in nature. We just may not have described or observed what that relationship is yet. Yet is the key. As soon as you say it doesn't exist and it's not there, you've just said, okay, I'm done. And that's like saying good. Ask Brittenham about the word good. I'm serious. Has he told you about the word good yet?
No.
When he worked with Pat Riley up in New York with the Knicks, Riley does not use the, is it Riley? No. Who's the Knicks coach that he worked with? Not Riley. Maybe it is Riley. The head coach of the Knicks.
Basketball person.
The head coach of the Knicks that he worked with when he was up in New York. And by the way, they won the world championship in all of this time. Never would use the word good with his players. He would never say good job or that's good. Because that implied that there was nothing more to do. There was nothing beyond. It's good.
There's nothing beyond good.
Yeah. So if it's good, the implication of the word good, I'm talking from where this perspective is. And the implication of good means that I've done it to a level that it needs to be done and there's no room for improvement or going beyond. So this head coach will never use that word. And if you notice, Mr. Brittenham does not use that word either. You think he does? Really? Good job. But he doesn't describe something as good. It's a little bit of a difference. Ask him what the difference is. So if I say to you there is a relationship between everything, and we just haven't described what it is or we haven't seen it, that's a yet kind of thing. There's a lot of stuff out there to be learned yet. Not by just you or me, but by everyone. Once we say we've learned it all, ooh, or there's nothing more to be learned from something, that's kind of a dead end. There's some that may seem to be dead ends. But, you know, think about the scientist who's been looking to come up with a cure for cancer, for example, and they research and they study this for their entire life. And they die having never found such cure. Does that mean that that's really the end? No.
For that.
For them, yeah. But do they quit too? Do they say, well, we're never going to figure it out, and they stop? Some people do. That's perseverance. I got a video on that too. You want to watch it?
Yeah, first, let's figure out 14.
Yeah, let's figure out. Hey, I like that. So if one, so you may not see a relationship. And I'm not necessarily just going to say to you, here's the relationship, because that's like opening up the box at the end and saying, okay, well, I'm about to die. I've been studying cancer my entire life. I deserve to know. So look in the back of the book and see what the cure to cancer is while I'm in my deathbed, and then I get to die knowing what it is. No, it doesn't work that way. Life doesn't work that way, you guys. It is, but if we get in the habit of constantly getting stuck and saying, I don't get it, and then looking for the answer, when you are in a situation where you don't have the answer to go and look at, it can be really frustrating. See, life is full of all kinds of questions where we don't have a definitive answer. We don't live in a cookie-cutter world where you're going to get a job, and every single time you run into a problem, you go to your supervisor and you say, well, what do I do here? And they say, oh, well, this is what it is. This is how to do it. Now they might tell you, well, this is where you find the toilet paper to go put into the bathroom that you're cleaning, because that's your job. But you might have another problem. You might get home and have water pipes that are frozen, and you don't just get to call somebody and say, well, what do you do? Because it might be different for every single house. And you might have a friend or a person you have a relationship with someday that you're having a problem with, and you're not able to settle the problem, get it ironed out. You don't get to just go to somebody and they say, oh, well, this is what you do, and everything becomes perfect. There's not a lot of square pegs that fit into square holes in life, and round pegs that fit into round holes. In other words, we don't have a simple answer to every problem that we come up with. So we put problems in front of you in school to get you used to thinking in different directions. Now, are you ever gonna have a job where you have to solve that problem? If you're a teacher, yes. But will you use the thinking processes?
We're not thinking that particular thing.
Not this particular thing, no,
But in general.
but relationships. Some of you may go into construction and building or engineering and design and architecture, I don't know. If you go into something like that, you will run into problems that will be spatial. All of you in life will have problems that you have to figure out, that will have a set of circumstances where things are related to one another and you need to understand that relationship. Whether they're objects, or their personalities, or your pets getting along with their environment or with you, whatever it is, there are things that will interact and you're gonna observe relationships. X, Y, Z, W, not necessarily, no. But this is practice. Yes?
Why don't we just have real world problems and just like do examples of what you could do instead of having that.
Yeah, why don't we have real world problems to be able to do that?
Yeah.
Yeah, I'd love to be able to do that. Unfortunately, it would probably require about 15 or 20 times as many teachers. It would require a school setting which would be your everyday life. And the expense of teaching people that way is really, really high.
To do it.
To some degree, there's degrees of that. Some families choose to do it with homeschooling. And they use experiences and they bring in the academic, formal things like this and apply them to those individual experiences. But it takes a lot of time. It takes a lot of commitment. There are some students that go to particular, like boarding schools, for example, where there might be one teacher just working with 4 or 5 kids. And they learn some of these procedural things and then they go out into the field and apply them. That's really, really expensive education. And we choose not to, at this time, afford to do it with all students. Would that be the best? Maybe. But then you miss out on things like basketball and hanging out with one another during lunchtime and seeing one another.
Why would that change?
Oh, why could you not see?
Well, you might be able to, but it would be a different way of organizing, being with one another. Why?
Well, if we had a different type of schooling, why would that change?
Logistics of moving people around. I mean, you just gotta, I don't know, you have to design it. Maybe it wouldn't. Maybe you could have it happen that way as well. But, oh, I know.
So much information without actually
I hear you. I agree. It's not a perfect system by any means. It's where we start though. And at the same time, to provide more experiential type things for you as learners requires more time for teachers. And I only have this many to prepare for every day. In other schools I've worked in, I've had this many, or this many. Some places have this many, and then it looks different. That's really nice. But then that gets boring doing the same thing 6 times in a day with different groups of kids. And there's trade-offs to everything. There's relationships to everything. So, back to the triangle. This, I think, is important. in pulling together what they're asking for in question 14, I guess it is. Because in question 14, they're talking about the measure of angle W, the measure of angle Z and Y, is that correct?
Yes.
Okay. What do you know that might be related to this? What could you say you know? W, Y, and Z, do they make a triangle? They don't. Sorta. So those of you that are doing sorta, what do you mean by that?
What point is W representing?
W is representing that angle.
So, they're all representing an angle, but they're also representing a point, right?
No, they're not representing a point. They are all representing an angle. All we're looking at here are angle measures. The measure of angle W is this one right here. So, can you say yes? Is it an equilateral triangle? It looks like it might be, but nobody has said that it is.
If it is, then W could be supplementary with Z or Y.
Oh, yeah. If it is. Yeah, if it's equilateral, these are all 60 degrees, and then this is supplementary to any one of those, true. But nobody has said that it's equilateral yet. So we cannot assume that. So that's kind of where we're at with this kind of geometry. We don't get to say, well, it sure looks like it, therefore it is.
What can you figure out if you don't know that Y and Z or Y and X are the same angle? They would have to be the same angle for you to really figure out anything except for X.
I don't know. I mean, it'd be helpful if you knew that, no doubt. But what do you know for sure?
X and W are supplementary.
Okay, we know X and W are supplementary right here. This we know for sure. So that's one piece of knowledge. What's another piece of knowledge?
Z, Y, and X about a 20.
Z, Y, and X, they add up to 180. X, Y, and Z, the measure of X, the measure of Y, the measure of Z is 180 when added together. That's the triangle sum property. And then we have supplemental angles. Supplemental, that's bad. Supplementary angles. We have supplementary angles. So here's something, and then we can say the measure of angle X plus the measure of angle Y plus the measure of angle Z is also 180. And if we write them that way, and we look at them, maybe we see something else. Maybe we look at the picture and see something else.
You can write like if statements, but
You can write what statements?
like if,
If?
like if X
Yeah.
equals Y, then W minus 180 is Y.
Yeah, if X equals Y. Let's try to stay away from ifs though and say what we know for sure. So in learning, we have kind of two groups of things that we do. One of the groups of things is called procedural things. I teach you procedures. You've been taught how to add numbers, right? 6 plus 4 equals 10. Seems elementary, simple, right? But it's something that you were taught, and that tool can be used to solve problems, believe it or not. I have 6 apples, you have 4 apples, we have 10 together. And those are the kinds of things you were doing like 8 years ago. but that procedure is still something that we're using, right? Measure of angles together. But then as you've gotten older and older, we teach you more and more procedures. And one of the procedures that I've worked with you on is the idea that this relationship here may be written in more than one way. That's one way to write it. But we can change how it's written and it still says the same thing, or at least there is the same relationship present. See, everything that's up there is relating one thing to another. Relating these angles to one another as a linear pair, or relating these two measures together as being equal to 180. Can we change that, the way that relationship is written, to say something different? And maybe use that bit of information to solve the problem. Yeah.
I think we might change it, meaning like, I would do like 180 minus the measure of x equals the measure of w. Like that.
180 minus the measure of angle x equals the measure of angle w. Is that true?
Yes.
All right, cool. There's a different way of expressing the same relationship. So we really only know two things, right? But if we look at them differently, maybe that helps. We still don't know what the measure is. We're never going to know what the measure is until we throw a number in there. But we'll know the relationship between the different angles. And that's what 14's asking for. What's the relationship between them? No, you don't get to measure. Your protractor is null and void. I know. Why do I make you bring them, huh? This is still what we're trying to do here. I want to move this. Still trying to find the relationship between these three angles, or a relationship that involves these three angles. No, not x, y, z. X, it's w, right? That's what I should have here. It's w, y, and z. Yes?
The measure of angle y plus the measure of angle z equals the measure of angle w.
Okay, hold up.
Well, if you're estimating that the measure of angle x is the same in both questions, then that would mean that the measure of angle w would have to be. Well, why would they be different?
So you said that x plus w equals y plus z? Is that what you said?
Z plus y equals w.
Z plus y is equal to w.
Yeah, because if you put those together on the line, then it'd make 180, and so it wouldn't.
Yeah. Because x would be the same measure throughout both questions. And so z plus y would equal w.
My brain just exploded. I can't believe you saw that. You saw that?
Get up there. Point it out. I can't follow you. Explain it. Nice and loud so they can hear it in the back.
It's pretty incredible. Go for it. No, it's good.
No. Okay. So,
Or you want to say it loud enough that we can hear it and I'll point out.
yeah.
Okay, go. Tell me.
Okay, if the measure of angle x is the same in both questions, like up there, then z plus y would have to equal w, equal 180.
So if x is the same, where? In here and in here?
Yeah, no, in that one and then at the top one, the very top.
This one.
Yeah, both of them,
So if x is the same, if x is the same here and here,
like the same measure.
it's the same measure. If those two are the same, then what?
Then y and z would have to equal w.
then these two together would have to equal
The same measure as W.
this. You're nodding your head. Can you prove it?
Yeah.
And I'm not saying it's wrong, I'm just saying, can you prove it? I don't see it yet.
Yeah, I
Yeah,
think so.
because, so if you added, Y and Z together, and then added, X, that'd be 180 for the triangle. And then if you added X plus W together, it'd be 182. So that means that Z and Y have to be the same as W.
Okay, so you look up here, here's X, here's X. Can I do this? Here's an X, here's an X. This is Y and Z. And this is W. So this number is being added to this. And down here it's being added to that. So whatever that is has to be equal to those two added together because they add up to the same thing, 180. Oh my goodness, I'm glad I have this on tape.
Do you?
Yeah, I do.
That's awesome.
Because in procedures is really, really, really big. That's really, really big. And you're gonna learn different ways to write and see that. And that is what, in my class that I take on every other Saturday morning for 4 hours online, 4 hours of Zoom with one bathroom break for less than 10 minutes. Oh my gosh, it's no fun. And it starts at 6 in the morning. But we keep talking about exactly this kind of problem, and how do you teach and get people to see this, and this is cool. So we take this fact and we take that fact, and you look, all of this is equal to 180. All of this is equal to 180. Therefore, we can say this is equal to 180, this is equal to 180, so all of that is equal to all of that. So look at what's in red there. Here's the inside of the triangle. Here's the linear pair. Here. And if you just get rid of X from both sides, then you have what Kate just said, that Y plus Z equals W. So let's see here, Y plus Z equals, whoops, other way around. Y plus Z equals W. Good, there's one answer. Is there another answer? What's that? You think there's another answer? See, that's not even what like if you said to me, okay, Dagan, I'm gonna give you $50, tell us the answer, and I'd roll over and give you the answer, that's not what I would have answered. And I got a hunch that's not in the key. It might be, it might not be. There's another answer that I can see, and I bet there's even another one beyond that. The relationship between W, Y, and Z. Yeah. I don't know, we're gonna sit here until we get it, but
So I kind of said the same thing as Kate said with
but with measurements, so you put like numbers in it? Yeah, and you know, that's a way sometimes to look at this. Sometimes we say, well, let's just turn it all into numbers. And then and if we can see how the numbers relate, then we can go back to the variables. Because variables are hard. It's a new way of thinking. You know, so if you said, okay, well, I'm gonna make this 40 degrees, make this 60 degrees. So let's see, then this has gotta be 80 degrees. This has gotta be 100 degrees. You just do that, and then you start manipulating the numbers and looking at how they're related to one another, you might be able to get to the same place. Or a different answer. Well, so far we know one relationship is for sure, that W is equal to Y and Z added together. We can prove that with algebra. She justified it with words. Okay, good. Your hippocampus just went and swelled a little bit. That's a region of the brain that she was talking about yesterday. All right, any more questions? We got to an answer. That's great. We don't have to have every single answer.
What's the other answer?
I'm sorry?
What's the other answer?
I'm not going to just give it to you. I'm sorry. I'm sorry? No, if I, it's like this. Hi, Stacy. It's like this. You're out there, you're trying to ride that bike, and I say, oh, just stay on top of the thing. Keep your balance. Lean the other way. Oh, now you know how to do it, right? Don't sit back when you're skiing. Keep your weight on your downhill ski. Now you know how to do it, right? You're really good. Jean-Claude Healy. He's one of the greatest Olympic skiers of the 60s and early 70s. So, yeah, we'll just make sure you don't hit the ball with the palm of your hand. Keep your fingertips on it when you're dribbling. Now you're a good dribbler, right? I just told you how to do it. Ball's got to go through the hoop. You just scored.
That's a little different than that.
No, it's not. It's no different. I'm sorry, it's not.
Tell us how we get there and then we figure it out.
If I tell you how to get there, you know the answer to one particular problem.
Well,
You
then
do
give us
not,
another problem and then you'll try to use that same.
yeah, but you're never going to see that exact same problem again.
Wait, can you share the
Ah. No, because there might be another answer in there, and then we just blew it for any of you that want to keep thinking about it. Okay. Time to reset. Do you want to ask me anything else from this lesson, Master? On perseverance? It'll take me time to dig it up, and I'd like to move you forward onto something which, yes, I am going to tell you this and this and this, but I'm going to try to explain the relationship, and then I'm going to let you persevere with it a little bit. Then don't put that lesson master away yet. Okay, just kind of keep it handy. But the next thing that we're going to go into is something called the distance formula. What are you laughing at?
Sorry.
This is vital, man. It's really crazy. The base of this is what Mrs. Dagan and I spent an hour and a half talking about this morning. We gotta go back to the geometry class today, and we gotta revisit this so that they can do some of their work. So, we have a picture. So if this is the bottom of Lake Michigan, what city is right up here? Chicago, very good. What's the name of your book? Who's it written by? There you go, University of Chicago School Mathematics Project. So everything's on, they have all kinds of stuff from this part of the country. Here's Indiana. What teacher in this building was born in Indiana? Who? No, not me. No, I'm not from Indiana. Never. Not a chance. North of Chicago. 2 hours north of Chicago. In Wisconsin. Mr. Davis? Mr. Davis is Indiana. He taught in Indiana. His first teaching job was in Indiana. Any teachers here from Michigan? Michigan.
Andreessen.
Mrs. Andreessen was born in Detroit, Michigan. Yeah. Somebody else, I bet there's another one. I don't know.
No, Miss Johnson, Minnesota.
Yeah, she's from Minnesota, Mr. Haas is Minnesota. Yes, land of 10,000 lakes, actually over 1 million, but that's okay. Here, they use this idea of the interstate highway to introduce distance. And I'm not sure how familiar you guys are with interstate highways, but they have mile markers just like we do here on the highway going up to Cluckwan. You know, you go to Cluckwan, that's at mile what? 22. So if you think about the highway, that's 22. Out at Fish and Game, there's a mile marker. 1. If you went a mile back from Fish and Game, you'd be down by Lutak Hardware. That's where it used to be mile 0, way back in the day. That's the very, very beginning where it turns into Beach Road. That's the beginning of the old Haines Highway. And then when they built the ferry terminal out there, they had, because it was a ferry terminal state, they had to have a state highway that went to the ferry terminal. So they added that. That's the new Haines Highway. But the problem is it's more than a mile out to the ferry terminal, so the numbering got all loused up. So 0 is down there, and 0 is out, what, by Picture Point or something like that? Something like, somewhere in that neighborhood. Yeah, and then they count miles out Lutak, so it's a little bit different. But anyway, they use mile markers on these interstate highways. And sometimes they go hundreds of miles across some of these states. You know, if you're out in Nebraska, there's a mile 400 and something, and things like that. And the question is this: what is the distance from Fish and Game to Cluckwan?
21
Wow.
miles. 21
Is
miles.
it 21, 22, or 23?
21.
Or 20? Who can make an argument for what it is? What is it?
I'd say it's 21 miles because you're already starting at mile 1.
You're starting at mile 1.
And that's, if you subtract that already, it's already there compared to where you're going, then you get 21.
So you take 22, subtract 1, that's 21 miles. Can we buy that? No? Let's make a number line.
Well, if you're going to mile 22 and you're not going all the way past mile 22, like, are you going?
0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 25. We don't need to go past 25 miles. Okay, so Cluckwan's at 22. There it is. Fish and Game is at 1. Each space, each interval is how long? 1 mile. How many intervals are there between Fish and Game and Cluckwan? Did you count with me? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1. So there's 21 intervals, 21 miles, 21 sections of the roadway that are a mile long. When you get to mile marker 2, you've gone a mile. When you get to 3, you've gone 2 miles, etc. So the distance comes from 22 minus 1. How far is it from Cluckwan to Fish and Game? How far is it from Fish and Game to Cluckwan?
21 miles.
Yeah, we don't walk backwards, do we? We go forward one way or the other. So whether you're looking at it going out or coming back, it's the same distance, yes? Okay. So if you're in Cluckwan, that's your starting point, and you take away your ending point. Yeah? Well, what if your starting point is this, and you take away, what does that equal? But it's still 21 miles, right?
Yes.
So here's what we do. if we say that the absolute value of 1 minus 22 is the absolute value of negative 21, what is the absolute value of negative 21? 21. So if we use the absolute value bars, it doesn't matter whether we're looking to the north on the highway or we're looking to the south. It doesn't matter where we start and where we end. If we take the absolute value, we will always get a positive number. We'll always get a positive distance. And with the distance formula, that's how we do our work. So, you know, here they've got all these mile markers on Interstate 80, and it's 80 and 90 together. And they say, like here, there's mile marker 21. And in South Bend, Indiana, there's mile marker number 77. So how far is it between Portage and South Bend? A lot is not. That's where you build a house. Is it 56? So if you take 77, subtract 21, it's 56. But see, sometimes we have more complicated math problems. And because of all the numbers that we're dealing with, we might take 21, subtract 77. And then you're going to get a negative number. So in math, what we do to correct that is we say, oh, let's see, I'm going to write in blue. We say that distance is equal to the absolute value, always the absolute value, of the difference between two different locations. That's something you should have written down. Distance is the difference between two different locations, and then you take the absolute value of that difference. So if you're in South Bend at 77 and you're at Portage at 21, it will not matter whether you take 77, subtract 21, or you take 21, subtract 77. If you take the absolute value of each, they are equal to each other. So this is a skill that we'll need to use. This is a procedure we need to use the distance formula. Do you guys have sticky graph paper? No? Do you guys have a straight edge? This stuff's nice because you can just put it right in, you know, where you want it. Yep. Hang on to it, okay? All right, so when you do this, think of the top half of this, because we might put two of them on here. But think of the top half of your little piece of graph paper and put some axes on there, X and Y. So the way this might look is if this is your piece of sticky graph paper, maybe what you do is work up here on the top half. Make sure you put your axes on the lines, label X and Y, use a straight edge, do your best to keep up. And I'd like you to plot 2 points. I'd like you to plot the point -6, 4, and 4, 4. a dot for each of those. You don't have to label them, just put them on the grid. And what we're gonna do is we're gonna say that each one of the little squares is a unit. So negative 6, 4, you need to plot negative 6, 4, and 4, 4. So if you just count boxes, how far are they away from one another?
The unit.
10 units?
Or 13.
And
So if you look across, they're 10 units apart? Yeah. And mine's gonna be a little more rudimentary. So I'm up here, and then I come over. 4, 4. Okay, so the distance between the 2 points is 10 units. Agreed? Okay, so then what I'd like you to do on your sticky note, even down underneath here, is I'd like you to write this out. So the distance, in this case here, is gonna be, and you're gonna write absolute value. If you wanna watch me write it all in, you're welcome to first. The distance is going to be the difference, so we're gonna use subtraction, between the two x values, because we're looking at a horizontal distance. So it follows the x-axis. So this is gonna be like x with a subscript of 2, subtract x with a subscript of 1. And what that means is one of the x values and then the second x value, they get subtracted. So then we're gonna keep writing with an equal sign and substitute the numbers in. So can you tell me one of the x values from these two ordered pairs? Negative 6? What's the other x value? 4. So this and this, these are our two x's. We're going to subtract them. So if we write this out as the absolute value, we have negative 6 subtract 4. So order of operations says that we have to first do the subtraction. Don't forget that. You don't turn them positive and then add them or subtract them. You take the difference first. So what is negative 6 subtract 4? Negative 10. Then the absolute value of negative 10 equals 10. It's important that we subtract first. Follow the order of operations. Okay, so that's one way to look at it. But you might say, well, I was going to say 4, subtract negative 6. So we could also write this, right? The distance is equal to 4 subtract negative 6 as an absolute value. And then the absolute value of that difference is still 10. So regardless of how we look at this problem, from left to right or right to left, the distance is 10 units. So one more. Can you make another grid on the bottom half? I don't see you for 2 days, do I? Wow. Okay. Yeah, I'm gonna send you out of here with homework, but it's gonna be the first 6 problems on the lesson master that I give to you. They're just like this. You'll be okay.
Many.
Oh, yeah, we had. Yeah, but that's.
So, first 6 problems on
Yeah.
this one. Yeah, they're different. So the first 6 on this one.
Wait,
You said we won't see you for 2 days.
Right, I don't see you for 2 days. You have 6 problems to do in 2 days.
no,
Tonight and tomorrow.
Yeah, you can do that.
what's it say?
You won't look for it. Oh, you might want your notes with, it's up to you.
I'll just see if the.
How would you do it if the Y coordinates are also different?
So are they meant to only do X then for homework, or are they doing the whole distance for
Oh, no.
So random.
Because they don't know the whole distance.
No, shoot, I thought these, oh.